Restall from the University of Melbourne, who is going to talk about an inferentialist account of identity and modality.
Thank you, Francesca, Luca, Leila, everybody involved in organizing this. I have loved every time that I have presented in seminars, either in Paris or in Amsterdam. And this is the first time that I have ever presented in both simultaneously, while not leaving my house in Melbourne. I mean, 2020, 2021. That's amazing. So if you want to download the slides so that you can see what I speed past, the URL for the slides is in the chat. The topic that I'm going to look at is what it said in the title. I'm going to look at an inferentialist, sequent calculus, hypersequent calculus treatment of identity and modality, and in particular their interaction. But the particular way that I will look at this is to show how defining rules, and I'll explain what I take defining rules to be, in a particular kind of hypersequent setting, I'll explain what that is too, can give a uniform proof-theoretic semantics of identity and modal operators like necessity and possibility, which allows equally naturally for modal operators for which identity statements are all necessary if they're true, and modal operators for which identity statements can be merely contingently true. That both options seem to be available to us and can be independently motivated. So that's the high-level picture. So the outline of the talk, I will give you some sort of philosophical background in the first section and introducing some of the relevant work about defining rules that I'll be looking at. Then we're going to look at identity. We'll just look at identity in a non-modal setting first. Then we'll look at defining rules for necessity, and then we'll stick them together. And then there's a little bit of homework at the end. So that's it. So here's the approach. The sort of philosophical background behind this is, well, you can ignore the philosophical background, but you don't have to. And if I'm talking to philosophers, the interest in this project for me is connected to sort of normatively pragmatic, semantically anti-realist and dialogical approaches to meaning. So what I mean by normatively pragmatic is looking at ways of defining concepts by way of their rules for use in a broadly Wittgensteinian or Brandomian sort of way. That means we're interested in rules for use. We're not pragmatists in the sense, or at least this approach is not pragmatist in the sense of analyzing meaning in terms of ways that things are actually used, but looking at the approach of meaning conditions for things being in terms of not truth conditions or representations, representational features, but in terms of rules for use. What makes this semantically anti-realist is that we're not focusing in the first instance to reference relations to objects or object-like things, whether they be, extensions of predicates or anything else like this. The semantics is given in some other way. That's what makes it anti-realist in that sort of realist, anti-realist schema. And finally, the rules are meant to be grounded in and meant to be able to constrain or apply to our actual communicative and dialogical practice. And in particular, I'm interested in the speech acts of assertion, denial, and inference. And so you can see this as a particular instance of the kind of work that Katerina's been working on over the last few years, and in particular in her recent book on the dialogical roots of deduction. So that's the sort of background in this. Now, where this becomes instantiated in terms of practice is this line about the sequent calculus that I've been arguing for, oh my goodness, at least 15 years these days, which says that one can think of these sorts of double line rules, which you will have seen either in Basic Logic by Giovanni Sambin or Kosta-Dozhan, or it goes back to hacking at the very least. You could think of these invertible double line rules as giving you definitions for logical concepts, where you can read these in that kind of normatively pragmatic kind of way, which says that you could introduce the logicians and by saying that asserting a conjunction has got the same force as asserting its conjuncts. So think of the things on the left as things that are asserted, things on the right as things that are denied, or if you like, things on the left as things that are asserted, and everything other than one thing on the right as things denied, and the thing in the focused slot being a thing that you are inferring from that background. Both of those approaches are kind of equivalent in given the structure of rules of contraction, weakening, and cut and identity, but we won't go into that here. You could just think of this as saying that if you've got some practice which involves a vocabulary that doesn't involve the logician's and, we could add the logician's and by saying that the force of asserting the conjunction is understood as being totally equivalent as the force of asserting both of those conjuncts. To deny a conditional, so if you read this in the denial reading, to deny a material conditional has just got the same force as asserting its antecedent and denying its consequent. Or if you like to prove the material conditional, thinking of that conditional as in the focus, you can suppose its antecedent, so add that to your stock of assertions and prove its consequent, because now the consequent B is in the focus position. There's lots of things that you can say about assertion and denial, and I can talk to you about those things later. I'm going to take all of that stuff as given, though, in this setting. What's interesting, though, is that you can do things with other kinds of logical vocabulary, not just the propositional connectives of conjunction, disjunction, negation, material conditional and stuff. You could look at the quantifiers and say that to assert to deny a universal quantifier, sorry for the typo here. I did not catch that typo. To deny a universally quantified statement, that's out of bounds if denying an arbitrary instance is out of bounds. Denying, or if you like, denying that everything satisfies A has got the same force as denying that N satisfies A for some fresh name N. So you can see this is sort of what we do with, universally quantified statements in dialogue. If I deny that everything has got some property, well, you could say, well, suppose that N doesn't have that property. And if I sort of refuse that, where N is basically a free name, which we could let be arbitrary, there's something strange in my refusing you to allow to do that. Or if you like, if you give that the proof interpretation to prove that everything's got some property, proves that an arbitrary instance has got the property, where you make no other assumptions about the term that's involved. So that's all, relatively understandable stuff. These things, on my view, count as definitions, and I'm not going to go into the background of this argument, but just, give it to me for the moment, or we can argue about it in discussion. But there are formal results which show that you can think of these defining rules as showing how to add the defined concept to a language which doesn't possess it, not by finding a paraphrase in the original language, but by making explicit something that was implicit in the individual, in the prior language. So we could, assert A and assert B, and, making explicit joint assertion by asserting this new unit, which we'll call their conjunct, is doing this job. Or, the duality between assertion and denial is somehow being encoded by the negation or by the material conditional, and substitution and generality is in some way being encoded by the universal quantifier. Well, that's sort of philosophically hand-wavy, saying this sort of makes explicit what is implicit. The technical results are that in controlled, well-behaved circumstances, we can prove that concepts added by defining rules like these are conservative and uniquely defining. In just the same way that definitions by paraphrase are. If I just define a term in a vocabulary by saying it's just a shorthand for some other term that I've got, that's going to be sort of uniquely defining if I wasn't equivocating when I was doing that. And it's certainly going to be conservatively extending, because I'm not really adding anything new. I'm just providing a shorter way of saying what I said before. Well, those two constraints of conservativity and unique definition, which is due to, Noor Belknap in his famous reply to Pryor's runabout inference ticket paper, those criteria, those constraints are satisfied by rules that are given by concepts that are given by defining rules like these. And I'll actually show you the structure of that argument, how that goes. So that's the sort of logical bones behind the rather flabby, hey, these things are making explicit, sort of philosophically hand-wavy comments. But one of the good things about doing defining like this is that the kinds of moves that I was gesturing at by these concepts are kinds of moves that we do when we are doing things that are in the ballpark of and not and if and all in our claims. But the logician's sharply defined concepts are still simple, well-behaved, useful, the rules can be followed, and we know what they are. The material conditional is not the if of natural language, but it is a really good thing for us to have in our conceptual toolkit. And they suffice for us in contexts where precision is valuable, like when we're trying to investigate the boundaries of mathematical proof, for example, or when we're trying to, stuff things in a database and figure out what's in the database, or just be careful. These defining rules sort of suffice for us to coordinate and communicate. And the technical background that's nice for you to know if you want to is that defining rules can give rise to standard Gensen style left and right rules in the presence of the structural rules of identity and cut. And the resulting rules allow for the usual cut elimination argument, which is how you get conservative extensions. The details of that in the case of, standard brand first order logic without identity and first order logic allowing for empty terms is in this paper of mine in the RSL from 2019, which you can have a look at. So that's the background. Now we're going to look at how to do identity. I'm just going to steal Steve Reed's inferentialist treatment of identity from this lovely little paper from Analysis from a few years ago by Steve. There's Steve. He does this in a natural deduction setting, but I'm going to stick it in the sequent calculus because this is going to be handy for what I'm doing. And I'm going to steal these rules because the rules look like this. Very strange rules, but one way of thinking about this, it's an invertible rule. It has got an identity claim on the right-hand side of the sequence. And on the left-hand side, we've just got the constituents of that identity claim, the A and the B, and the other terms that were in X and the other terms that are in Y, the other sentences that are in the sequent context. But what we've got left there is this strange predicate, which is floating free, this F. And this F stands to predicates in the same way that the eigenvariables in a quantifier rule stand to the universal quantifier. The eigenvariables being what's an eigenvariable? Well, it's an unbound variable, or if you like, it's an inferentially neutral constant or term. The crucial feature of that inferentially neutral constant or term is that any singular term in the vocabulary satisfies or is constrained by any of the inference rules governing that singular term. The idea is that the thing is semantically arbitrary. Same thing here for this F, except it's a predicate. It's a predicate, but it's a predicate which is just a free predicate. And in particular, the constraint here is that F is absent from the lower sequent in this invertible rule. So there's a two-premise invertible rule. What that means is if I can prove from FA to FB in the context where the other X stuff is asserted and the other Y stuff is denied. Oh, and by the way, I can prove from FB to FA, making no other assumptions about A and B, about F. The only way that could happen is that if A is identical to B. Okay, so that's reading it from top to bottom. Reading it from bottom to top, if you deny that A is identical to B, then there's got to be some feature that A has that B doesn't, or some feature that B has that A doesn't. Either of them would do. In fact, we've got both. So thinking about that, in terms of the meaning of identity, denying that an identity is true has the same significance as taking there to be some feature that holds of A but not of B, or vice versa. Or if you like, to prove that A is identical to B, prove FB from the assumption of FA and vice versa, where you make no assumptions about the predicate F. Okay? That's a rule. It's skirting extremely close to doing second order logic because it looks like I've got something that I'm quantifying over, but there's no quantifier binding that predicate F or anything like this. But as we know, first order logic with identity is sort of skirting at the boundary between first order and second order logic. So, but sort of conceptually speaking, the idea is that identity is a kind of indistinguishability. And that seems reasonable. It's not indistinguishability in terms of some feature that we already have in our language any more than saying that the universal quantifier rules in standard natural deduction or the sequent calculus doesn't identify the meaning of the universal quantifier with every instance being true, where the instances are the names that we actually have. No, the instance is arbitrary in the premise. Same thing is happening here. So it's not saying that we can access some feature that A has that B doesn't. No, it's just saying that there is some feature that A has that B doesn't. Well, there's lots that I can do with this, but what I'm going to do is show you, here's an example derivation in a system which has the defining rules for identity in it, and we'll show that identity is symmetric. There's a couple of other rules that are involved in this derivation along the way, which I will tell you about along the way. But let's just have a look at this derivation and focus on this part here. We start with an axiomatic sequent. The axiomatic sequence are just sequence with the same thing on the left as on the right. And then we apply the defining rule from bottom to top. We sort of take the rule here and say, well, because when these hold, that holds, and vice versa, when this holds, if A is identical to B and FA, then we've got FB. And so that's the rule applied in that direction. Now, we've got this free variable f, which is hanging around, and in a system which has got, in a proof system which has got, eigenvariables, in this case, they're eigenvariables of predicate term. I tried to emphasize the phrase eigenpredicate when, writing these notes, and I checked. Eigenpredicate does not exist on the internet anywhere. It's never been, there, indexed by Google, and I think I would like to keep it that way. So hopefully no transcript is being, generated for this talk. But if you have a system with eigenvariables and these invertible defining rules, then you need something which says that if you prove something about f, then, well, because it holds of the predicate f, it can hold of any predicate at all. And in particular, I'm going to say, if it holds of f, it will hold of the predicate of being identical to A. I'm going to be completely explicit, rather than assuming that every sentence with a slot in for a singular term can automatically generate something of predicate kind. I would rather say that let's use lambda abstraction to generate things which are syntactically predicates, just to be completely explicit of what's going on. So the specification rule says that if I've got some sequent which I can derive, I can globally replace any of these special basic predicates with any other predicate in the vocabulary, and it's still derivable. Now, that kind of rule of specification is the kind of rule that you don't need in the standard sequent calculus. It should be admissible, okay? And in fact, once we convert this into a rule, into a system which is a proper left-right sequent calculus rule, we will show that this is admissible, this rule. But if we're doing things in terms of a defining rule like this, which when read from bottom to top introduces these free predicate variables, then we need something to go from that to more specific cases. So let's just have the rule of specification for the moment. And so what we get from A is identical to B and FA to FB, we apply that to the obvious predicate is identical to A. Well, if A is identical to B, and if the predicate is identical to A applies to A, then it also applies to B. And then, well, we are going to, in this part of the proof, prove first that A is identical to A, and then use the defining rule for the lambda abstraction, which is what you would expect to allow you to convert sentences to lambda abstracts so that they become, you focus on the term that is being described and package everything else up into being a predicate. So do that, use the defining rule for lambda abstraction to introduce the lambda, and then we do a cut on, the property of being identical to A applies to A, so we can cut that out. And then we get the property of being identical to A applies to B, and indeed you get that A is identical to B. Tells you that B is identical to A as you'd expect, just from this defining rule, not needing to impose symmetry of identity out of anything else. So, but that should give you an idea of how the rules work. And they're those rules. Now, I promised that we were going to go from this to the sequent calculus, which is a little bit more familiar, which should give you a sense of the kind of sequent rules that we're using. Well, one of these defining rules is a right rule. It tells you how to introduce an identity on the right. That's just what it is. And so we take the rule from top to bottom. It's the right rule. How do you make the left rule? Well, these are the left rules. And these are the left rules where P is now any predicate in the vocabulary at all. How do you get that from the right rules? Well, you start with an identity, an axiom, A is identical to B gives you A is identical to B. You unpack the identity that was on the right, because that's the thing that we can define using the defining rule to give you FA gives you FB. Then you generalize from F to whatever predicate P you like, and then you cut on P given by an arbitrary context, and you cut on the PB given by an arbitrary context. And that tells you, since that is given by an axiom, that here is how you can derive an arbitrary sequent with an identity on the left. You need to...
Sorry, Greg.
Yep.
There is a question for you.
Oh, yeah. Is P any predicate in the vocabulary? Yes. P is any predicate in the vocabulary. Good, Giorgio. That's a terrific question. And you should think, my God, that's probably a problem. Yes, hold on to that thought. P is any predicate in the vocabulary, including lambda predicates, including complex lambda predicates, which might pack a whole bunch of other stuff. Okay? Yes.
Yes, thanks. Whereas the F in the
F is a primitive atomic predicate.
Atomic. Thank you.
It's atomic, and in particular, it's inferentially neutral. In particular, it can't be the identity predicate. Even though the identity predicate is an atomic predicate, it's not inferentially neutral. So it's got to be an arbitrary atomic predicate. Okay, so here P is any predicate at all. So we're going to have a hell of a lot of these rules. So hold on to the thought, which if you do cut elimination and things like that, you're probably going to have. But this is how you generate a left rule. And this is a kind of algorithm. Start with an identity sequence, unpack the defined term by means of the defining rule on one side. Then if it's got any terms which are kind of inferentially special, generalize them to anything else of that kind. And then for all of the other bits that are left, cut them away. And that's what gives you the other premises. And you can see in Generality and Existence 1, I go through that for all of the defining rules of the other things to generate standard Gensen-looking left-right rules. And so do it in either way, you get these two rules. Okay, the obvious question that you might have is, okay, can we eliminate cut? We now got a system with left and right rules. Can we eliminate cut? And this rule of specialization from an F, a predicate F to some particular predicate P, can we eliminate that? And the answer is yeah, cut in, and both of these are eliminable. In particular, the spec rule is height preserving admissible in the system, which has got the left-right rules and cut. You just get a derivation which has got a specification appealed to, and then you show that all of the rules, if they've got an inferentially neutral predicate F in the conclusion, you could have just substituted for that in all of the other rules and it would still be a proof. And so you could just, instead of proving instead of deriving, X gives you Y, you could derive the thing where the F is substituted for P in a proof of exactly the same structure, in a derivation of exactly the same structure. Won't go through the details, they're kind of boring. Cut's eliminable in the system with the left and right rules too. You just take your introduction of an identity on the left and an identity on the right, and you look at them and you just perform a substitution and the cut's eliminable without having to introduce the identity. It all works. You're just actually sort of inverting the derivation of the right rule from the defining rule. But eliminating cut hardly seems worth it because we don't have the subformula property. In particular, you look at these P's, which are above the line here, they could contain any bloody thing in the language at all. So we don't have the subformula property. I mean, these rules look a heck of a lot kind of like a weirdo version of cut, which says take any formula like in any formula applying to A, which I've proved, and any formula applying to B, which I use as a premise, I can cut them out at the cost of assuming that A is identical to B. So yeah, how am I going to get the subformula property? We got violations of the subformula property everywhere. I mean, here, that's not too bad because they're sort of weirdo logical predicates, which are sort of content free. And you might think that we can sort of hold our nose about, but these, my goodness, violations of the subformula property everywhere. What are you going to do? If you want to have analytic derivations, derivations which satisfy the subformula property, we need different rules than these. Okay, well, first we're going to get rid of the right rule, and it turns out you can replace the right rule by your good old friend reflexivity, that A is identical to A. Turns out anything you could prove with the identity on the right rule, you could prove with this. It's very straightforward. First, we can prove this from the identity on the right rule. It's just one-step application. On the other hand, if I'm applying identity on the right, and instead I want to appeal to reflexivity, here's what I could do. I've got a derivation where I'm applying identity on the right. I could prove that A is identical to A, and then take my proof that from FA to FB and apply that to the case where F is the property of being identical to A. Because this is carrying, any feature that A has to a feature that B has. Well, I know that A's got the feature of being identical to A. So, and I can prove that, if A's got a feature, so does B. So I'm going to prove that B's got the feature too, namely that feature of being identical to A, and we're done. And so, yeah, there's got a cut in it, but we can eliminate the cut if you like. And you can, this is height preserving admissible specification as well. So in general, restricting ourselves to the reflexivity axiom from the identity on the right rule is no problem. What about identity on the left? Well, it turns out we can replace identity on the left with a whole bunch of axioms. Because if we looked at the identity on the left rule, we said it kind of looked like cut, except it was sort of saying that we could get from PA to PB at the cost of saying that A is identical to B, or we can get from PB to PA at the cost of A being identical to B. Well, let's make them axioms. You can get from PA to PB if A is identical to B, and actually, and vice versa. So impose those as axioms in our proof system for the moment. And then we show that we can, well, these follow from the left and the right, the left rules, but then from those, you can recover the left rules by means of the application of two cuts. So if I instead now float all of the identity claims up to the leaves as axioms, this is all sort of known in sort of sequent calculus treatment of identity. I'm just doing it in a very sort of general setting here. If you float these axioms up to the identity facts up to the leaves, then we can then have all the things that we wanted to do with the powerful but violation of subformula property rules all over the place by replacing them. The reflexivity thing by something involving a cut, and the identity on the right rule by reflexivity and cut, and the identity on the left rule with the left axioms as axioms and cut. So then you might think, well, yeah, but imposing axioms which have got a whole bunch of complicated vocabulary in them as extra axioms, that sucks. I mean, that's still, you know, a violation of analyticity in some sense, even if it's happening up there at the leaves. And this is the point at which we kind of notice that you can, by induction on the structure of the predicates, restrict these axioms to the atomic predicates in your vocabulary. You know, here's a case showing that if I've got a lambda conjunction predicate, I don't need to impose that axiom separately because the conjuncts, it follows from the conjunct things using the conjunction rules and lambda abstraction. Same thing for negation, it swaps the polarities around. Same thing for the quantifiers, etc., etc. So you can restrict the axioms to appeals to these identity axioms where the predicates are primitive. Now, I've just written that as PA, but that's actually any n-place predicate with an A in one slot and a B in that slot. Okay, substituting from A to B or from B to A. And now we can take our derivations, just use the axioms, eliminate cuts from the derivations, and the cuts using the standard cut elimination algorithms. And that's going to push the cuts up until we get cut on our axioms. And now we've got to do something because the axioms, identity on the left and identity on the left, of these left axioms, which have just got the forms that I've got written here, and the reflexivity axiom on the right. Now here, you know, that's an axiom, but this is a cut on two axioms, and it's not itself an axiom. Okay, what am I going to do? Well, you know, I could add that to my family of axioms, and it suffices to close these axioms under cut. I mean, you could say you could only have cut on axioms. That's totally fine. That's one way of doing things. But a nice way of talking about what these identity axioms should be is like this. Each axiom, this class of sentences, this class of sequence, sorry, where I've got any collection, in this case, a sequence, just a multiset of identity statements which links A to B. So IAB is just any bunch of identity statements where there's a path from A to B in the obvious sense. Just splat out all of the terms and draw a path between them undirected when between term 1 and term 2, if I've got T1 identical to T2 or T2 identical to T1. And then IAB is just any of these multisets of identity statements where I've got a path linking A to B, and I've got a primitive predicate involving A and another primitive predicate which involves B. Oh, and by the way, the definition of linking is just a little bit more complicated. Let's just say that the empty multiset links A to A, so I don't need to use that. So in fact, the old axioms, PA, therefore PA, count just by themselves as instances of this class. Yeah, A identical to B links. Oh, this is just another sort of inductive definition of the thing that I just told you, represented in terms of graphs. Oh, and by the way, we could leave PA out if it was A identical, if it was A is identical to A just by itself. So that in fact will give you, that's a class of sentences which is closed under cut. Which gives us all of the axioms that we have. So what you get for looking at identity like this is sort of an inferentially motivated notion of identity, which could be understood as a defining rule at the level of this, which says, here are conditions under which I'm going to tell you the force of denying an identity statement. Denying an identity statement has got the same cache value as distinguishing the things that you're denying are identical. And so that's what this defining rule has got. And that's got the virtues of applying to an identity statement in an arbitrary context. So it tells you what to do with an identity statement on the right-hand side of any sequence, doesn't have any conditions on what's in the X and what's in the Y there. On the other hand, we can also, I have gone to the next slide and the screen has not caught up. So I've got to stop my sharing and start it again to refresh it. The connection just got lost there. Sorry about that.
Sorry, Greg, there is also a question for you.
Excellent. Is it problematic to introduce a transitivity rule on the left instead?
I mean, instead of the kind of sequence that we have of A equals to B, B equals to C.
So it's not going to do everything that we want to do. I'm still going to need, so, I mean, the transitivity rule is if in the form A is identical to B, B is identical to C, rules that we have here. So it is not, if I just have that and the primitive left axioms that I had at the beginning before I started closing it under cut, then the class is still not going to be closed under cut. And if you're happy to have cut, left up to the axioms, that's fine. If you want to have a specification of the class of axioms, which is already closed under cut, which is what I was just pointing at here, you could do that. It's 6 of one, half a dozen of the other, really. But what we really do need is some things which are connecting the identity claims and the other predicates in the vocabulary. That's what's really important. And that's what the second thing is doing here. One way of thinking about the axioms is that they are semantic constraints concerning primitive predicates, in the same way that I might, for example, introduce into my vocabulary gradable predicates. And I might say that, if A is F'er than B and, if B is F'er than A and FA then FB, that's a nice way of introducing sort of gradable predicates into a sequent vocabulary like this. And this is semantic constraints governing primitive predicates, where this is the, at least as F as thing, which is connected to effing, whereas identity is connected to all of the predicates in this way. And that's one way of thinking about things just at the predicate level. And then it's a sort of a sanity constraint on the other rules that it generates the defining rule. On the other hand, you've got the defining rule, and then it's a kind of sanity constraint on the other predicates that it actually sort of is equivalent to this. But that's two different ways of looking at it. Okay, that's identity. And yeah, in this setting, they're equivalent as far as derivability goes. But you're not here for just identity. We're interested in identity and modality, and I've got like 20 minutes to do that. So let's do this. But I want to notice that what we're doing here kind of relies on identifying in your vocabulary what's a singular term and what's a predicate and what's substitution. If I've got a vocabulary and I know what that is, and certain kinds of substitution are admissible, all of the stuff in the background, then this counts as kind of logical in the sense that, if you and I agree on what's a singular term and what's a predicate and all of that stuff, and you introduce identity with the defining rules, and so do I, then they're going to be interderivable with one another. Okay, that's kind of cool, but it relies on that. Okay, necessity. Okay, the next bit is going to be pretty quick, but I'm going to say some sort of philosophical background. Now, modal reasoning. What does modal reasoning depend on? Well, I reckon modal reasoning trades on the kind of supposition and context shift that happens in discourse all the time. I say Oswald shot Kennedy, but we might be, running various scenarios and thinking about what would have happened had he not. I might say, suppose Oswald hadn't shot Kennedy. What would have happened then? And we, do some thinking and talking and asserting under that kind of scope. On the other hand, I might think that Oswald shot Kennedy, but you might not. And I might say, well, hang on, suppose you're right. And suppose he didn't shoot Kennedy. Then what? And so this is another supposition. So in both cases, in the discourse, we've got kind of positions where in one part of the discourse, I've granted that Oswald shot Kennedy. I'm committed to Oswald shooting Kennedy being holding, yet I'm opening up a kind of possibility of Oswald not shooting Kennedy. But I think these two kind of shifts are different. One of them is a kind of subjunctive or metaphysical, if you like, how things could have been had things gone differently if Oswald hadn't shot Kennedy. We try various scenarios on. How would history have gone then if Oswald hadn't shot Kennedy? What would have happened then? Would he have been around when people landed on the moon? That sort of thing. Would he have, got a second term? All of that stuff. On the other hand, indicative epistemic shifts different views of how things could actually be, often given some kind of background body of evidence, which we keep fixed. If Oswald didn't shoot Kennedy, then, well, Kennedy was shot, so who did? That's a different kind of discussion that we're having. Now, possible world semantics is really useful in modeling both of these sorts of kinds of modal notions, sort of subjunctive possibility and sort of epistemic possibility too. You know, some of you are in Amsterdam, it's kind of an, you know, an Amsterdam industrial complex of, you know, using modal logic, and in particular, using possible world semantics to model both of these sorts of things. But I want to look at proof theoretically. And the view that I'm sort of trying to push is that a modal operator stands to a kind of context shift in the way that a quantifier stands to a category of terms. And so the general shape of a hypersequent like this, where I've got a box statement on the left-hand side of a turnstile now separated from a statement on the right-hand side of a turnstile, separated by this kind of bar representing a context shift, is saying, you know, I've asserted that A is necessary, and then I've shifted context and denied A. Or if the thing which is in the focus there is something that I'm trying to prove, maybe I am proving A in that context from the assumption that A is necessary in this context. And this is the job of a box statement, to provide a kind of passport or a visa, allowing a claim to get from one context into another. So that's the idea. And so a defining rule for an identity, for necessity, can go like this: to deny that A is necessary in an arbitrary context where other stuff is asserted and other things are denied, you kind of open up a new context where you deny A. So if I deny that A is necessary, I suppose that it might have not happened. Consider it not happening. Now, that might be understood subjunctively if we're thinking of subjunctive context shift, had that not happened, or that might be a kind of epistemic context shift. Suppose where this box represents some sort of epistemic necessity, and we're saying, well, suppose that's not the case. Suppose that, as a matter of fact, you know, not actually deny it, but suppose, you know, that's not known, or suppose, you know, suppose we try denying that given our evidence that we're keeping fixed or whatever. Anyway, denying that A is necessary has got the force of denying A in some context, or to prove that A is necessary, you prove it in an arbitrary context where you make no other assumptions about what holds. And so necessity is a kind of a passport that allows for preservation across contexts. But indicative shifts define a kind of epistemic necessity. Now, these kinds of boxes that you have here in a hypersequence system like this is not sort of epistemic necessity of the kind of follows from what we actually know. Because here, I'm not assuming anything is happening in these kinds of other zones. This sort of stands to epistemic possibilities in the same way that a kind of S5, you know, truth in absolutely any possible world operator stands to sort of metaphysical possibilities. This is something more like a kind of a priori knowability or something like that. You know, holds in any epistemic circumstance unconstrained by our evidence. The S5 necessity holds in any possible world unconstrained by our prior commitments about particular things that have happened. So it's your backtrack as far as you like, because I'm just talking about that stuff. The form of the rule is the same in either case. The content differs. And in particular, what you get is S5. I mean, this is a hypersequence system for S5, but thought of in terms of a defining rule. I'm not going to go through the details. Here is how you can use the defining rules in the hypersequence system to get you the characteristic S5 axiom. If something's not necessary, then it's necessary that it's not necessary. Because these zones are just treated as a kind of a multiset where, you know, anything is possible relative to anything else. We're not imposing any kind of, you know, tracing points of origins, or, you know, talk to Francesca about trees and more complicated structures if you want to do more complicated modal systems. But both kinds of shifts are important to critters like us. We disagree, we've got reason to come to shared positions, and we plan, we've got reason to considering options prospectively or to replay scenarios retrospectively. So disagreeing sort of corresponds to epistemic shifting. Let's say, well, suppose you're right, suppose you're right. Let's try your position on for size. And planning corresponds to sort of subjunctive shifts. And we're just formalizing this in the way that logicians do. And the neat thing about this You don't need a sort of prior commitment to an ontology of worlds. That sort of comes. Now, you can combine these two kinds of context shift into one hypersequence system easily enough, but I'm not going to have time to talk about doing both of these in the one system. References contain that paper. From these defining rules, you can get left-right rules. I'm not going to talk about that here. One defining rule, the defining rule from top to bottom is the right rule. And to get the left rule, you apply the defining rule on an identity and cut on an arbitrary sequent to get an obvious kind of left rule, which says if you want to prove something from A, instead you could prove it from the claim that A was necessary somewhere else. You know, that's a reasonable left rule. And you can eliminate cut and do the usual things. But I want to, in the remaining time, talk about combining identity and necessity with those two interpretations, the sort of subjunctive metaphysical and the epistemic in mind. And the worry is you just jam the two things together, you get necessary identities automatically. Just plug in the defining rule and take my proof, which went from A is identical to B is identical to A, but instead don't apply it to the assumption that A is identical to A. Apply it to this, the thing that we can prove, that it is necessary that A is identical to A, or A has got the property of being necessarily identical to A. And then any feature which holds of A holds of B. So if A is identical to B, then it's necessary that A is identical to B. Bam, identities are necessary. And so if you're Tim Williamson, you say, aha, identities are necessary. That's just what there is. Then modal logic is going to tell us a hell of a lot of interesting metaphysics. You can read this in your own time. It's a lovely, lovely quote, which kind of says that any of us that do anything about contingent identities are uglifying, weakening, and complicating things without reason. Okay, it's opinionated in Tim's inimitable style. He says that if you're going to try and modify your logic when logic tells you that identity is necessary on the basis of some ontological or metaphysical scruples, then that's a bad thing to do. Well, I think there's some wonderful work. Giovanna Corsi's wonderful sort of summary paper on counterpart semantics and Maria Aloni's lovely paper on individual concepts in modal predicate logic have got interesting motivations and definitions, for example, of things that you can do with modal logics with contingent identity. Now, let's just take an example. I'm going to focus on the epistemic case. Hesperus is phosphorus. You know this, I know this, they're Venus. But we did not always know this. And when somebody denied that Hesperus is phosphorus, they're not being inconsistent. We discovered that Hesperus was phosphorus. Imagine we're Babylonian astronomers and I think that Hesperus is phosphorus and you think that it isn't. And I might say, well, suppose you're right. And you might not be inconsistent in doing this. You might have some theory of what's going on, et cetera, et cetera. It's an epistemic possibility for us. So what to do with this sort of view of things? Well, the crux of the matter, proof theoretically, is this. Is it consistent to grant that A is identical to B in one context while distinguishing A from B in the other? That's the question. That's what we want to know. And I reckon when it comes to indicative shifts and disagreement, this is totally consistent. When I have the epistemic interpretation in mind, this is completely consistent. We learned that Hesperus is phosphorus. The possibility that Hesperus wasn't phosphorus is open to us. We were not inconsistent in denying that. Somebody that denies that Hesperus is phosphorus can say that Hesperus is the evening star, phosphorus is the morning star. There we go. And Hesperus isn't the morning star and phosphorus isn't the evening star, et cetera, et cetera. Subjunctive shifts, when it comes to planning, I reckon there's a way of understanding the motivation to think that identities are necessary. After all, when I think of planning contexts, if I take it that Hesperus is phosphorus and I'm wondering where I would end up if I travel to Hesperus, then of necessity, I'm going to phosphorus. Okay. If I wonder what would happen were Hesperus to have been, destroyed by aliens, 2 days ago before any of us noticed, then phosphorus has been destroyed by aliens because it's Hesperus. Okay. When I think of the kind of shifts that are involved in kind of planning subjunctive possibilities like that, there's a case for this. So I'm not saying that the cases are watertight in either case, but what I'm going to try in the remaining few minutes is to say, what would happen if we said that identities were indicatively, epistemically contingent and subjunctively metaphysically necessary. And see, can we run both of those things in one go? And this is where we just say, okay, Tim, where in modal logic as metaphysics do you say the word epistemic? And this is the one place he doesn't care about epistemic modal logic. And so, okay, there it is. Okay, how do I do subjunctive context shifts with necessary identity rules if I'm going to do my identity rules in the way that is sort of logically most well behaved? It kind of goes like this. To deny that A is identical to B, that is the same as denying that, saying that A and B are distinguishable, but we don't need to distinguish them in this context. Distinguishing them in another context would be equally fine. That's the right kind of form of an identity rule. And this will give you, when you do exactly the kind of grindy work that I was doing in the first section, can also convert them to axioms, the reflexivity axiom, now holding in any context at all. And this rule, the identity on the left axioms, which says that if I've just got a bunch of sort of a network of identity statements, now in any zone of a hypersequent, they can all jam together to tell me that if A holds, if P holds of A, then it holds of P in some zone. So this is the identity statements are kind of profligate. They've got a passport to go anywhere they're necessary. And you get the usual sort of constant domain quantified modal logic, motivated in this sort of inferential kind of way, which says that to deny that A is identical to B is to take that A and B are distinguishable. Okay. And here's a cut-free derivation, just using the axioms. Now this counts as an axiom because A is identical to B is kind of a little network linking A and B. And now that A is identical to B on the other zone is now linked with that as an axiom. So that's one of our axioms, and that means we can introduce the necessity, and away you go. So there it is. Okay, in the remaining 4 minutes, I'm going to tell you why and how to resist this move for contingent identities and the epistemic interpretation. We want to block this move. We want to block the move which says that if A is identical to B, if I grant that A is identical to B, then if we indicatively shift, then asserting FA and denying FB is out of bounds. We want to say, no, you know, I'm granting that A is identical to B, but now this is an epistemic position which might be denying that A is identical to B. But we want to still derive this in the case when they're in the same zone. And that's going to be a little bit tricky because we also want to deny this when it comes to an epistemic modal. Because after all, we want to reject the claim that if A is identical to B, and if A has the property of being known to be identical with A, then B's also got that property. Because that's going to, you know, the epistemic modality is now going to give these identity statements passports to go over there. So we want to derive this guy. Let me just highlight this. We want to derive this guy in the appropriate senses while blocking that one. What that means, I think we go back to the motivating idea and to say that, well, to distinguish A and B, we want to find some feature that A has that B lacks. That's still how I distinguish things. I say, well, this can't be that because here's a feature that A's got that B doesn't. But epistemic modalities don't generate features. You know, being known to be identical to A is not a feature that A has that B lacks. It's a predicate, but it's not a feature generating predicate. Okay. So what we need to do is we need to have in our vocabulary two kinds of predicates, a class of feature predicates and a class of general predicates, if you like. You don't have to have the class of general predicates in the vocabulary as atomic general predicates, but I like vocabularies that are closed under kinds of substitution. I don't like the kind of view which says that the only way to generate general predicates is by means of epistemic modalities. So let's have two classes of predicates. Feature predicates are closed under the classical connectives and quantifiers and lambda to generate them. And applying lambda into an epistemic modal context creates a general predicate, but not a feature predicate. But there might be other feature predicates too. You might think that, being famous is a feature predicate or something like that if you don't want to analyze, or is a general predicate that isn't a feature predicate. If you think that you could analyze that as involving a kind of epistemic component. And then there's going to be two kinds of specialization rule, one for feature predicates and one for general predicates, because general predicates satisfy fewer conditions. And then you can have these contingent identity rules looking exactly like where they are before, where F's are an arbitrary feature predicate, and still works. Get the usual sorts of axioms, grind through the results. You can have a defining rule, left-right rules, cuts eliminable, subformula property for the thing with the identities as axioms. And here in these things, P's got to be a feature predicate rather than a general predicate. General predicates involving epistemic models. And so to take A to be identical to B is to take, to deny that A is identical to B is to take that to be some way to distinguish A and B, and that involves a feature. So if you want to combine these things, have a two-dimensional sequence. I thought I should show you that. What are these rules like in the remaining minute or two? And then I'll give you your homework. The modal rules are conservative and uniquely defining relative to a choice of context shift. If we fix on what the context shift is, these count as kind of logical relative to that. If we introduce box twice, given the same hypersequence separator, the operators are equivalent. The necessary identity rules are conservative and uniquely defining, given the choice of predicates in the language. If two identity rules are added using the same form of rules, they're equivalent, provided the identity predicates count as predicates for the purposes of the analysis. And the contingent identity rules are conservative and uniquely defining as well, relative to the choice of feature predicates in the vocabulary. And in particular, if I add them twice, then they're going to be interdefinable if at least I see that your identity counts as a feature, and so does mine. And so you get the interdefinability inferences happening. Okay, I should say something about models. I'm half in Amsterdam. You can't talk about modal logic without talking about models just a little bit. Here's the models. The slogan is fill out an underivable hypersequence, fill it out, make it fatter and fatter and fatter, and the thing that you get in the limit is a model, is something which describes a model. Process of filling out involves these sort of reformulated versions of cut and the modal rules and the other rules, which kind of say that if I've got a sequent, then either, if that's not derivable, then one of the things it comes from can't be derivable. So that's going to force A to either occur on the left or on the right. This is kind of a sequent-focused version of the Henkin construction, where, if a box formula is false at this sequent, then there's got to be some zone inside the sequent where the thing under the box is false. That's reading that box rule backwards. So in the limit, the zones correspond to the world. The formulas on the left-hand side of a sequent are true, and the formulas on the right-hand side of a sequent are false. You just do the propositional stuff, you get universal models for S5. It's straightforward. The necessary identity models are pretty straightforward. The identity predicate determines an equivalence relation on terms, and its extension is fixed across each of the worlds. So we just get constant domain S5. It determines a congruence relation for each predicate at the world. That's what the axioms do. They say that if A is identical to B, then every predicate applying to A has got to also apply to B, because we could never have A holding of predicate holding of A but not of B. So that's what gives identity a congruence relation. So we can quotient out the terms to form your domain, if you like, and the expected truth conditions hold for all the operators, and you get constant domain S5 with necessary identity. Models for this, for the necessary identity rules, are exactly what you would expect. Constant domain, quantified S5, if you add the quantifier rules, which I haven't mentioned. Now, here is a hypersequent which turns out to be underivable, just involving identity. I'm not going to explain why it's underivable, but I will show you what happens if I sort of trace these zones in the limit. What I've got here is at least a world and a world and a world. In this world, A is identical to B and C is identical to D, but B is not identical to C at the very least. And in the next world, B is identical to C, but A is not identical to D, because that's on the right. And here, A and B and C are all identical, but A is not identical to D. So none of those are identical to D. So at the very least, what I get in these models are kind of local equivalence relations on the class of terms, equivalence relations at each different world. And so that's what the extension of identity is going to be such a thing. Now, this is kind of a, one way of thinking about a model, but mostly when people think about models of things with identity like this, they like identity to look like identity, not just an arbitrary equivalence relation. So what we could do is quotient out at each world, and you'll get something which looks like this, where at one world, I've got two things, A, which is identical to B, and C, which is identical to D. At this next world, I got at least three things. At this world, I've got two things. And the extension, if you like, of the term A is a kind of choice of these objects at each domain. And so is B, and so is C, and so is D in the usual sort of way. Now, there is nothing in the sequent calculus that I've given which forces the size of the domain to be the same at each world. And there's nothing in the sequent calculus that I've given which forces there to be much of any kind of constraint about which kind of individual concepts the singular terms have got as their kind of extension over each of the worlds. But let me say something about the predicates. If I get a feature predicate like F, a feature predicate like F has got to hold or not of things at each of these worlds. And so here I've just said that F holds of A and B and holds of at this world and holds of A and it holds of D at that world and it holds of A, B, and C because they're all identical at that world. Okay, that's what a feature predicate has to do. It's basically got an extension at each of the worlds. What does a general predicate do in this? Well, a general predicate can have a different value at each world for each of the individual concepts, for each of the choices that you have. And so here, for example, we could say that G holds of A, but not of B, even though A and B are identical. And G holds of, because it's a general predicate, not a feature, holds of A here, but not of B, and holds of A here, but not of B. In particular, I chose that G in this case was, it's necessary that X have property F. That's G of X in that case. And so the extension of a general predicate is just given by choosing a set of individual concepts at each world, while a feature predicate is given by setting the underlying objects behind the feature concepts at each world. So the models look sort of standard. It's a very weak kind of modal logic with contingent identity. Picture that you get here is that identities can be metaphysically necessary but epistemically contingent. We'd like to have a way to resolve disagreements about identities, and they're the kinds of things that we can learn by engagement with the world around us, but they're open to us until we learn them. And that's a way of motivating that once we've learned an identity statement, we use that to constrain how things could go or how things could have gone, so make them subjunctively necessary, but make them epistemically contingent. To define identity, we require preservation of features, but not preservation by predicates that introduce epistemic shifts at the very least. Okay, so I said we'd have some homework. Here's the things to do. I haven't actually done anything with quantifiers. The usual quantifier rules can be added, but I think the interesting work to do with quantifiers in the contingent identity system would be to look at various views of sortals and conceptual covers, because the interaction of quantifiers and individual concepts is very, very interesting. And this is where I'd refer you to Maria's work as one example, and actually some quite old work is Anil Gupta's Logic of Common Nouns. Has got some really interesting work to be mined in this kind of setting. The existence predicate I haven't talked about, obviously something which could be added, and comparisons with the kinds of strength that you can get. In particular, this is a very weak base system of sort of contingent identity. It would be nice to know, firstly, how to make things stronger in terms of broadly sequent rules, but then which of those kinds of principles making things stronger count as defining rules, on my view, is an interesting thing for me to look at. So, there's some references for lots of things for you guys to chase up. Thank you very much for your patience.
Thank you.
Thank you.